Talk of the day and of the week, Kostya will tell us more about integrability and determinants.
So these are beta equations that describe the spectrum of the Heisenberg spin chain and also the spectrum of the SU2 sector of superannuals at one loop. So I'll discuss the classical limit of these equations. So we studied the bound state solutions and well, some simple classes of solutions. So there is a limit in which these equations become exactly solvable. And this is the classical limit. Or this is the same as considering macroscopic spin waves. So since magnons are interacting bosons, we can put an arbitrary number of them into the same quantum state. In other words, we can Bose condense them, and this Bose condensate of magnons just describes a propagation of a macroscopic spin wave through the lattice. So spins precess sort of classically with phases that change in space and time. So the spectrum of such spin waves can be found from the beta equations. So we know that if we put a finite number of magnons into the same state, they will form a bound state that's described by the string solution of the beta equations. So let's consider the case where the string is macroscopically large. So we take the limit where the length is infinite, but also the number of magnons is infinite such that the filling fraction is fixed. So, and we also consider these special solutions where roots, so the solutions of these equations are called beta roots. They sit in the same strings, and if strings are macroscopically large, they start to curve in the complex plane. So they form some contours on which they sit. Now the distance between the roots, as we learned, is of order 1. But then the momentum of each magnon, which is roughly speaking is 2 pi n over L, will scale as 1 over L. So we will take the limit in which the mode numbers are finite. And are of order 1. And consequently, the momenta scale as 1 over L. So we consider bound states of very low frequency magnets. Now that the rapidity variable is defined as 1/2 of cotangents U over 2, which is approximately equal to 1 over p for such small momenta. And so the rapidity scales as L, so it's very, very large. So what we can do is we can rescale it back and introduce the x variables, which are finite in the large L limit. And now in the x-plane, these very long strings become continuous contours because the distance between the roots in the x variables are of order 1 over L. So they form continuous distributions, but these distributions are concentrated on some contours in the complex plane. So there are several contours on which the roots are distributed. So each contour corresponds to the wave number. If you excite, say, 3 wave numbers, then there will be 3 contours, etc. Now, the distribution can be characterized by continuous density. So this becomes continuous. And thus, if we have a sum of some functions of beta roots, that becomes an integral along this set of contours of this density. Where C is just a collection of contours. Now, if you take this limit in the beta equations, so they can be written in the logarithmic form. And to the first approximation, they become just a set of these equations that okay, there's something so should also write 1 over L here. So after we take we replace the sum by the integral. And since here the summation doesn't include the same root, we can replace it. We should replace it by the principal value integral. Okay, x. So we get a singular integral equation for the density of beta roots. Now, this equation can be solved in general in terms of hyperelliptic functions. I will not describe this solution in any detail, but once we have all of these solutions, we need to impose some normalization conditions. And then we can calculate the anomalous dimension by considering some particular moment of the density. So now, important thing to notice here is that the energy of these solutions is still very small. It scales as 1 over L in the larger limit. So they are smaller by a factor of L squared than the bare dimension, which is just L. Any questions? Yes?
And the second normalization condition on the right hand side is 2 pi m or 2 pi m?
2 pi m. Yeah, m like a mother. So,
What is M?
what is m? M is an integer. It's so this condition comes from the condition that total momentum is 0, but in the lattice momentum is defined up to 2 integer multiple of 2 pi. So, in principle, it can be equal to 2 pi times 20. Okay, so no questions. Well, then let me describe the solution of the SSX spin chain that describes all possible scalar operators. Now, again, there is a beautiful mathematics behind this that includes this Young-Baxter equation and algebraic beta ansatz, which I will just skip and write down the answer. But before that, I'll give the physical motivation why the answer looks precisely like that. So the basic idea is this, again, this scattering picture. So we look at the ground state. The ground state is just the same trace z to the L, but now there are more excited states because we allow all possible scalar operators. So we first look at small deviations from this ground state that will be magnons, but now magnons can carry flavor because we can insert arbitrary scalar operator. We can replace z by any other field. There are 6 fields, so we can replace it by 5 other scalars. And so we can look at the scattering of these flavored magnons, find this matrix, and basically the beta ansatz describes the diagonalization of this scattering matrix of magnets. But first of all, we need to decide what the elementary excitations are. And the first idea that there are just 5 of them, and they correspond to insertions of various scalars that propagate through this vacuum of z's with certain momentum. So the ground state is trace z to the L, and magnons are operators of the type z, then some field phi, z, and then sum over x with the plane wave function. So this is position x. So in this phi, at first sight, it seems that phi can be anything of w, y bar, w bar, or z bar. So there are 5 modes. So we might think that there are 5 possible types of magnons. Which turns out to be wrong. So this counting doesn't work. To understand how the correct counting works, I need a little bit of group theory. So we shouldn't think about states, but rather we should think about operators that create these magnets. And in the SU2 case, these operators are just sigma minus, sigma lowering operators. So we hit the ground state by sigma minus at some point x, and then some overall sites with certain wave function. So here we can do the same. We can consider lowering operators that act on each of the sites, and they will create the magnet states for us. So, okay, and we know how to define lowering and raising operators actually for any Lie algebra. So the basis which does this is called Chevalier basis. So in any Lie algebra we can choose the basis that consists of Cartan generators, so this will be a little sort of reminder of basic group theory. So we can choose Cartan generators and raising and lowering generators E. I will denote them as E plus minus. So these are called positive or negative roots, negative simple roots. The index alpha runs from 1 to the rank of the Lie algebra under consideration. And then the whole Lie algebra can be generated by repeated commutators of positive or negative simple roots. So the defining relations are written as follows. So H alpha with the root is so the roots are eigenstates of Cartan generators. So there is no summation over beta here. Then if we commute positive root with a negative root, so most of the times we will get 0, but if it's the same, if these roots have the same label, then we get the corresponding Cartan generator. And finally, we should impose the condition that repeated commutators of simple roots give 0 after some finite number of steps. So these relations are sometimes called Serre relations, and they completely define Lie algebra. So we start with the simple roots, and then we can generate all other roots by commutators. And this relation tells us when to stop, when we don't get anything new. Okay, so the only sort of entry that defines this relations is this set of integers that's called a alpha beta. So this set of integers form a matrix that's called Cartan matrix. So Cartan matrix completely defines Lie algebra, and the classification of Lie algebras reduces to classification of Cartan matrices, right? With matrices with right properties that make these cell relations self-consistent. Okay, so representations can be built the following way. And so this applies to any finite dimensional simple Lie algebra, such as SO6. So since Cartan elements commute, they can be diagonalized in any irreducible representation. So their eigenvalues are called weights. And in the Chevalier basis, the eigenvalues are called Dynkin labels. So mu alpha is a set of Dynkin labels. Now just from commutation relations, it's clear that positive and negative roots simply add, or they just shift. They shift the weights by corresponding, I guess, coulombs or by corresponding rows of the Cartan matrix. And so weights are also integer numbers. So by starting with the weight that is annihilated by all positive roots, we can, by applying negative roots, we can build all vectors in the representation. So this status is just the highest weight. And the Dynkin labels of the highest weight are called Dynkin labels of the representation. So we can characterize the a representation by the Dynkin labels of its highest weight. So now all other states are generated by repeated application of negative roots. So let me call this Q. So we start with the highest weight and apply negative roots until we get 0. So thus we generate everything. So for SO6, So, okay. Actually, the linking labels can be arbitrary positive integers such that at least one of them is not 0. So this characterizes all possible representations. Usually this can be summarized in terms of the linking diagram. So, for example, for SO6, the Cartan matrix has this form: it's 2, minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 2. That corresponds to this form of linking diagram. So the circles here correspond to diagonal elements. So the circles, each of the circle corresponds to a 2 on the diagonal, and links correspond to minus 1. Sort of connect various diagonal elements. So there is a link between element 1 and 2 that's denoted by this arrow, and also there is a link between these two nodes of the linking diagram. So we can characterize representations by assigning integers to all nodes of the linking diagram. So this is the well-known construction. Now to relate it to a more convenient or easy to visualize representation, where we have, say, okay, so if when we assign charges G1, G2, and G3, such that Z, Y, ZW, Y have charges 1, 1, 1, and their conjugates have charges minus 1. So this corresponds to eigenvalues of SO6 rotation in sort of 3 independent 2 planes in 6-dimensional space. They are related to these linked labels in a simple way. So Q1 is J2 minus J3. Q2 is J1 minus J2, and Q3 is J2 plus J3. So this is SO6, or equivalently SU4. Now let's consider the vector representation. So the ground state in the vector representation with the highest weight state is Z, and then various rotations can produce all other, we start with this vector that, okay, it's a complex vector, but it's obvious that by rotations we can get anything else from this, all other 6 scalars. So this, let's consider this as the highest weight. Then it has charges in the G1, G2 basis, it has charge 1, 0, 0. If we go into the Dynkin label basis, then we see that this has labels 0, 1, 0. So this representation has 1 on the middle node and zeros on the outside nodes. As a matter of fact, if we these representations that have ones here and 0 in the middle correspond to left and right spinors.
How do you know that the Hamiltonian that you get from the perturbation theory has to do the vector representation?
Because
From
such
the
is my Hilbert
very
space. I started with fields that transform into vector representation. So it's not a property of the Hamiltonian, it's property of the Hilbert space. Okay, so let me actually draw how the states are obtained by lowering operators. So if we start with the this state 0, 1, 0, that's Z. Then the rules are very simple. So you just subtract possible rows of the Cartan matrix to get all other states. So on that state we can only act by E2 minus to get 1, minus 1, 1. And then it's easy to convince oneself that this is W. Can you see this easily? Well, I think it's pretty obvious. You just so W in that basis is 0, 1, 0. So if you do this linear combinations, you get precisely that. Now, if you on that state we can act by E1 or E3. So if we act by E1, we get minus 1, 0, 1. That's Y. Then we get 0, 1, 1, 0, minus 1. That's Y bar. I think I should be made a mistake somewhere. That should be 0, minus 1, 0. And this is Z bar. And we cannot go further, so Z bar is the lowest weight in the representation. It's annihilated by all P minuses. So an obvious idea is to define our states of the spin chain to be just the simple negative roots. So the simple negative roots are creation operators, since we start with the highest weight. So the ground state is z to the L. And then we can define creation operators for magnons. Just from the lowering operator setting on possible sites. So now, since Fourier transformation is just a change of basis in this, in the space of operator setting on the spin chain, it's a linear, non-degenerate linear transformation. By applying an appropriate number of these lowering operators, we can get any state. These form a complete set of operators with which we can generate the complete Hilbert space. So applying these operators sufficiently many times, we can reach any point in the Hilbert space of the spin chain. Now, this an obvious guess would be that these states create our magnons, and since the label alpha runs from 1 to 3, we get 3 elementary magnons. Associated with the various possible just simple roots of the algebra. So, do you think this is correct? Okay, so the answer is that this is also wrong. Why? Well, the reason is very simple. Is that you see that operators E1 minus and E3 minus annihilate Z. So if we act by A1 or A3 on the ground state, we get nothing. It just annihilates the ground state. So they cannot create anything. So what do you think, how many elementary excitations are there in the spin chain? Yes?
One.
No? Any other ideas? 2. No. You have the last chance.
Oh.
Who said that? You got right. You got it right. So indeed there are 4 elementary excitations, and they're constructed as follows. So it's sort of the correct picture is intermediate between this naive picture of fields that can propagate on the lattice and this more group theory structure when we use lowering operators. So what we do is we start with the ground state, and then we follow these arrows in it's in Lincoln diagram. I actually don't know how these diagrams are called. Anyway, this set of possible states in the vector representation. So first we can act by A2 on the ground state. So we put some excitation on the middle node. And that creates a state that has many z's and a w somewhere in between. Now, as you see, we can act by E1 and E3, but most of the time that would do nothing because it annihilates Z. So it will act only on this side and will turn W into Y or Y bar. So if we act by, say, A1 on this state, which is to say, put an excitation here, what we'll get is the state in which we'll have Y in this sea of Z's. Okay. So this creation operator A1 has a sort of auxiliary role. It doesn't produce an independent excitation, just flips the flavor of the magnet. So if you have an existing magnet somewhere in the spin chain, the A1 will change its flavor. So if we act by A3 on A2 on the vacuum, so that produces Y bar. And okay, we can also act by A1 and A3 simultaneously. Which will make a W bar. Now, if you want to get the Z bar, we should add another excitation on the middle node. So that is to say, we act by A2. So I suppress here the momentum labels. They at this level they're just irrelevant. So we put two excitations on the middle node. So indeed, if this operator acts on this side, then it will produce the Z bar, but it will produce also a large number of times it will act on Z, and it acts non-trivially. So most of the time it will produce another W. So it will produce Z, W, Z, 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 W, Z, etc. So it will produce two magnets. So basically this state contains two magnets. And Z bar should be regarded as a composite excitation. So it's when these two elementary magnets with flavor that is just W overlap and sit on the same side. Now it's allowed for them to do that, but then they produce, so what it means is that they produce Z bar. So Z bar is not an elementary excitation, it's a composite stuff. So so it's a composite field if you wish. Not as a field in N=4 pyramidals, but just in the spin chain picture. So in total there are 4 excitations that are created in this. So that these elementary modes are W, W bar, Y, and Y bar. And we can create them by first creating W and then acting by these flavor changing creation operators. So this describes how the elementary excitations look like.
I guess the second W should be W bar.
No. So let's see. So A2 is a linear combination of A2 minuses acting on various sides. So if A2 minus hits Z, it produces W from that table. If it hits W bar, it produces Z bar. If it hits anything else, it produces 0. So this is just a bookkeeping, but it sort of explains what the spectrum looks like in terms of elementary excitations. Now, if it is actually not specific to SO6, if we study a spin chain with arbitrary symmetry group and an arbitrary representation on the side, the picture will be absolutely the same. So, yes?
You need to know the Hamiltonian, how the Hamiltonian expressed in terms of...
Right, so this is just a kinematical description. And then there is the following statement that there is a unique integrable Hamiltonian that acts on the nearest neighbors where the Hilbert space is the product of certain representation of certain symmetry algebra, so that H L plus 1 acts on the tensor product of this representations into itself. So, and the ground state, let's assume that the ground state is the highest weight in this representation. So now I just write down the solution without derivation for this Hamiltonian. So I will not write down either the Hamiltonian, it looks rather complicated for arbitrary group, nor will I explain how to diagonalize it, just write down the solution. So if we have a Dynkin diagram, and representation is characterized by a set of Dynkin labels, then we can associate creation operators with each of the nodes of the Dynkin diagrams that correspond to simple negative roots. And these excitations can carry these creation operators carry certain momenta. This momenta will be characterized by rapidities. So at each node we will have say k excitations characterized by rapidities. And states are just labeled by assigning various number of rapidities to each node of the Dynkin diagram. So the beta ansatz equations are equations on these rapidities, and they only depend on the group entries. So they're completely characterized by the Dynkin labels of the representation in the Cartan matrix. So this is the most general beta ansatz that we can write for nearest neighbor interactions on the spin chain. I think this result was derived by Dievetsky and Reshetikhin sometime in the 80s. So you see that beta ansatz has a very clear group structure. Once you give me representation and the Cartan matrix, I can write down the beta equations that will diagonalize the spin chain.
Does this work for any Lie group? Or
Sorry?
Does it work for any Lie group or simply laced groups? Or
For any Lie group, yes. And in fact, it includes even it also includes non-compact Lie groups, so representation can be infinite dimensional. Then the only requirement is that it starts with some highest weight. Yes, so the total momentum is obviously the left-hand side of the beta equation. And the energy is given by the sum of all rods. So it's immediately clear that only beta roots for which Q alpha is non-zero carry energy and momentum. The other roots are auxiliary. So there is a small, there is one important point. So it doesn't mean that if we add an auxiliary root that just changes flavor of the excitations, the energy of the state will not change. That's not true. Because the beta equations contain interactions between various roots. So indirectly, through affecting these momentum carrying roots, it will shift the energy of the state. Once we know the roots, the only roots with non-zero Q enter this sum for energy and momentum. So let's do some examples. So, well, let's return back to the SU2 case, but make it somewhat more general by considering spin S representation at each side. So the Cartan matrix is trivial, and it's just equal to 2. It has only one element. And then we have a representation that have Dynkin label to S. So the beta equations contain only one type of roots and have this form. So it's I S uj minus is to the L equals the product of k not j uj minus uk plus I uj minus uk minus I. So for S equals 1/2, we are back to the Heisenberg spin chain. But this diagonalizes more general Hamiltonian. Another example is SO6. With the vector representation. So there will be 3 types of roots, U1, U2, and U3. So only this will carry energy and momentum. And well, you can write down, so there will be 3 sets of equations that describe interactions of various types of roots. So as you can see, interactions, so roots of type U2, for instance, will so their beta equations contains 2 pieces. It contains the momentum piece and the scattering piece. So the momentum is determined by the Dynkin label. So only U2 roots will have non-trivial left-hand side. Now on the right-hand side, we will have scattering between various roots. And any roots scatter on themselves. So because the diagonal elements of the Cartan matrix are equal to 2. But they also scatter on the roots with which they are connected by the link of the Dynkin diagram. So say U2 roots will interact with U3 and U1 roots. U1 roots will interact only with themselves and with U2 roots, etc. So you can easily reconstruct these beta equations for C6. And they will describe the spectrum of excitations for the SO6 spin chain, and consequently the spectrum of anomalous dimensions for scalar operators.
But I think I missed something. You showed that this is a natural spin chain associated to SO6. Did you show that it follows from n equals 4 simply?
So yes, from n equal 4 we got the spin chain that's integrable. Now this spin chain is unique. There is no other integrable
Oh, that wasn't just for SU2 that it was integrable. You showed that it was integrable.
for SO6. Yes. So and consequently it falls into this class of spin chains which can be diagonalized by beta ansatz.
Can you show this directly or just through the integrability?
Well, there is of course a derivation of these equations, but it's sort of complicated. I think direct derivation is complicated. As a matter of fact, this type of beta equations is called nested beta equations. This is just a terminology. For some reason, they are called nested. Okay, but then this construction suggests how to generalize it to the complete set of operators. Well, we just replace the group. We say that we go from SO6 to PSU2 to 4. We know the Cartan matrix of this algebra. So we'll write it down. Now, for superalgebras, Cartan matrices are a little bit different than for purely bosonic. Group algebras, in particular, they contain so-called fermionic roots. So the fermionic. Well, they're called fermionic roots, but in fact, they correspond to. Okay, so some of the diagonal elements in the Cartan matrix can be 0. And then so this will be -1, -1, 2, 2. So the Dynkin labels are, well, first of all, there are two special features of these super Dynkin diagrams. They contain fermionic roots, zero diagonal elements, and they are not unique. So Cartan matrix of whatever basis you choose. So Cartan basis or Chevalier basis is very, it breaks. It's very non-invariant. You choose specific elements. So you choose, for instance, sigma 3 as when you choose sigma 3 as the Cartan matrix, you choose some direction in space, so that you say that z direction is special. So it's in principle you could have chosen sigma 1 as the Cartan element, but these are all related by symmetries, and in the bosonic case the Cartan matrix is the same in every basis you choose. That's not true in the fermionic case, so there are some rules how to transform this Cartan matrix from one basis to another basis.
The first entry, how there is a minus 2, is it?
Sorry?
The first entry in the Cartan matrix.
-2, and the last actually also -2. So past the fermionic root, this pattern changes, so the diagonal elements become negative and off diagonal positive. So this particular Dynkin diagram looks like this. So this is basically the SO6 subgroup, and obviously the highest weight that we should take is 0, 0, 0, 1, 0, 0, which uniquely fixes the beta equations, and it turns out to be the right answer. The beta equations for this diagram describe the complete set of anomalous dimensions at one loop. So I have almost no time to describe any solutions to these beta equations. Let me just tell you that the elementary excitations of this spin chain well, they correspond to, you can easily count what they are, like we did for the SO6. So you necessarily put one root here, and then the Cartan matrix tells you how much roots you can put on the other nodes. So the rule is such that the middle node should always have more roots than the outer nodes. So this describes the physical states of the spin chain. And okay, if you count the elementary excitations, then you find that there are 16 of them, and 8 of them are bosons, 8 are fermions. So the statistics goes as follows. Once you put something on the fermionic root, that changes statistics. For instance, if you put one beta root here, one here, one here, that would describe a fermion. If you put one root here, 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 and here, that will be again a boson. So the statistics is determined how many times you cross the fermionic root on the spin chain.
For XO6, we know the expression of the spin chain in terms of the generators. Do you know in this case, in this general case, the form of the spin chain?
Yes. The Hamiltonian is known. It's not very simple, but one can write it down. So we can summarize the states in a form of a matrix. So okay, first of all, we learned that the bosonic SO6 excitations are this Y and W fields and their conjugates. and they are naturally can be represented by an 2x2 matrix. So we can introduce one left index and one right index that takes two values each. So there are four complex excitations in total. So this follows actually from the symmetry breaking of SO6. That's actually that is equal to SO4, and that breaks to SU2 cross SU2 by the ground state. So since the ground state is not a singlet of SO6, the symmetry is spontaneously broken or non-linearly realized, and excitations are transformed under a small group, which is SU2 cross SU2. So this is just the scalars that we can insert in the chain of Zs. We can obviously insert covariant derivatives, so we can act on this phi's by d mu, and then as usual, it's convenient to contract it with this sigma matrices. So there is another set of four. So there are four SO6 excitations, and there are four derivatives that we can act by. So there are in total 8 bosonic excitations. Now fermionic excitations correspond to components of they are obviously describe fermion fields, and so fermion fields carry this alpha dot indices and also SO6 indices. And if you do carefully the analysis, you realize that the components that are elementary excitations are have one dotted, one undotted index. So we can draw this in the form of a diamond. A dot. And so along the diagonals of this diamond, so the diagonals of this diamond are related by supersymmetry transformations, which form two copies of PSU2 algebra. So the unbroken supersymmetry is PSU2 cross PSU2, and so this would be a good point for me to stop, because this PSU2 squared symmetry has wonderful consequences for the non-perturbative spectrum of unequal force Mills, which will be described by Kikos Bazik next week. So I'll stop here. Thank you.
Are there any questions?
Could you say something briefly about how much of this survives, let's say, at 2 loops? I mean, can you write down beta
How much of
index
this?
equations, exact beta index equations for 2 loops?
So 2 loops. Well, let's talk about all loops. So at all loops, you can write down beta equations that are a little bit more complicated than that. And they are characterized by sort of a brother of this Dynkin diagram that corresponds to a different basis in the Lie algebra. These beta equations are asymptotic in the sense that they are corrections for finite change that they don't capture, because these equations assume that all interactions are local, and so we can use beta ansatz, so the scattering picture that we use turns out to be exact. Now, interaction range grows with the order of perturbation theory, and at some point it starts to overlap with the spin chain, which is called a wrapping effect, so that the interactions wrap around the full spin chain, and then we lose the control over this simple picture with the beta ansatz. So the beta equations that are currently known, they are exact for infinitely long chains, so they are non-perturbative in lambda, but they are perturbative in the exponential corrections. So they do not capture effect of order e to the f of lambda L. And in fact, f of lambda is known. It's 2 arc sinh e square root of lambda. So given any operator, we can compute its anomalous dimensions with this accuracy.
I mean, to what extent can you apply any of these ideas to multi-trace operators?
Almost to no extent, because multi-trace operators is a 1 over n effect, and I don't know how much of this survives beyond the leading order and the large unnamed.
You could find a ground state product of traces over Z.
That's right, but yes, that's right, but they mix with the single trace operators only through 1 over n diagrams, so this mixing is suppressed as 1 over n. So in other words, to the leading order in 1 over n, the anomalous dimension of a multi-trace operator is a sum of dimensions of each of its trace components. But then there are corrections in 1 over n which were studied in some particular cases just by brute force without the use of integrability.
No sign of integrability.
There is no sign of integrability if one looks for some simple signatures of integrability. So there is a rather interesting, there are interesting degeneracies associated with this integrability that has to do with the fact that so this conserved charges, they form abelian algebra, so there is no, by itself it cannot predict degeneracies. All multiplets are one-dimensional. But some of these charges are C even and the others are C odd. So if we include charge parity, then the algebra becomes non-abelian. So there are this parity, so some operators that are parity even and parity odd are degenerate, which wouldn't have been expected on general grounds. Now 1 over n corrections leave these degeneracies. So this means that in the literal sense integrability doesn't work beyond the leading order and 1 over n expansion, but perhaps it's just this, the signals that it can be used in some other way.
Any other questions? Okay, let's thank Kostya for a beautifully created Have a good weekend. See you Monday.